In America alone, tens of millions of locks are produced every single year. How exactly is a lock made? What goes into crafting something that must be strong enough to stop thieves, precise enough to work flawlessly thousands of times, and durable enough to withstand years of use? Today, we're going to take you deep inside the world of lock manufacturing. From raw metal to finely crafted mechanisms, we'll see step by step how locks come to life, and the process might surprise you. Because behind every lock is a fascinating combination of metallurgy, machining, precision engineering, and even art. Before we jump in, don't forget to like, subscribe, and hit that notification bell so you never miss more eye-opening documentaries about how everyday things are made. Now let's unlock the story. Locks have been protecting people for over 4,000 years. The very first locks date back to ancient Egypt and Mesopotamia. These were simple wooden mechanisms, often with pins that could be lifted by a specially shaped key. Although primitive by today's standards, the idea was revolutionary, a barrier that could only be opened by someone who had the right tool. Fast forward to the Roman Empire, and locks evolved into more sophisticated metal devices. Romans were some of the first to use metal wards and keys, sometimes even wearing small keys as rings on their fingers for convenience. In the United States, companies like Schlage, Kwikset, Yale, and Masterlock transformed lock manufacturing into a large-scale industry, supplying everything from padlocks for soldiers in World War II to deadbolts for suburban homes in the 20th century. Understanding this history is important because modern lock production combines centuries of knowledge with cutting-edge technology. And with that background, let's step inside a factory and see exactly how a modern lock is made. At the heart of every lock is metal. Most locks are made from brass, steel, or zinc alloys. Brass is especially common because it's strong, resistant to corrosion, and relatively easy to machine. The process begins with large shipments of raw metal arriving at the factory in the form of bars, rods, and sheets. These materials will eventually be shaped into the body of the lock, the shackle in padlocks, and the intricate parts inside the locking mechanism. Before anything is cut, the metals are tested. Factories use spectrometers to confirm chemical composition, ensuring that the brass or steel meets exact standards. A weak alloy could mean a lock that fails too easily, something manufacturers cannot risk. Once the raw materials are ready, the real transformation begins. The body of the lock is its backbone, and it starts with either casting or forging. For brass padlocks, molten brass is poured into molds shaped like the outer shell of a lock. These molds are made of steel and can withstand extreme heat. Once cooled, the solid brass forms a rough lock body. For heavy-duty locks, steel plates are stacked together in layers, laminated steel locks. These plates are stamped and pressed into shape using hydraulic presses that apply tons of force. After casting or forging, the lock bodies are cooled, trimmed, and then sent for machining. Machines drill precise holes where the cylinder will sit, where the shackle will enter, and where pins and springs will eventually be placed. It's here that accuracy is critical. A fraction of a millimeter out of place could mean a lock that doesn't open smoothly, or worse, one that can be easily picked. By this stage, you can see the outline of a lock, but without the mechanism, it's just a chunk of metal. The real magic is still to come. The heart of most modern locks is the pin tumbler mechanism, invented over 170 years ago and still going strong. Now here's the genius. When the correct key slides in, its unique pattern lifts each pin to just the right level. This aligns all the pins at what's called the shear line, freeing the cylinder to turn and unlock. Each pin is just a few millimeters long, Yet factories produce them by the millions with stunning precision. High-speed machines cut, grind, and polish pins from brass rods, ensuring uniformity. Once all the parts are ready, skilled technicians or automated assembly machines carefully load the pins and springs into the cylinder. It's like putting together a tiny puzzle with dozens of pieces, except this puzzle must work flawlessly every single time. Of course, a lock is nothing without its key. Keys are typically made from brass or nickel-silver alloys. The process starts with blank keys, flat pieces of metal cut into a standard shape. These blanks are fed into key-cutting machines that use a combination of milling and grinding to carve the exact pattern known as the bitting. Each notch corresponds to the height of a pin inside the lock. Even a small mistake, a notch too deep or too shallow, would result in a useless key. After cutting, the keys are polished, sometimes nickel-plated for extra durability, and stamped with identifying marks like the manufacturer's logo. At this stage, the lock and key are paired together, tested, and adjusted if necessary. Now they're a perfect match. Locks endure constant use, so quality control is intense. Many locks are plated with chrome, nickel, or even powder coatings to resist corrosion. Outdoor locks might get extra treatments to withstand rain, snow, and extreme temperatures. Each lock is tested mechanically. Machines may insert and turn the key hundreds of times to ensure durability. Shackles are pulled with thousands of pounds of force to check strength. In some cases, locks are exposed to salt spray to simulate years of weathering. Engineers also test locks against tampering, picking, drilling, or forcing open. If a lock doesn't meet standards, it doesn't leave the factory. Only after passing all these checks are locks packaged and shipped worldwide. The journey of a lock is a story of precision, durability, and trust. It's amazing to realize that behind every lock on your door, there's an entire industry working to keep you safe. If you enjoyed exploring how locks are made, don't forget to like this video, subscribe, and hit the notification bell so you never miss more behind-the-scenes documentaries about the things that shape our world. Every day, as we walk down the busy streets of our cities, most of us hardly notice the cast iron circles embedded in the pavement. We may step on them, drive over them, or see them lined across sidewalks, but rarely do we stop to think about their purpose or their extraordinary durability. These are manhole covers. Far more than simple lids, manhole covers are silent guardians of the infrastructure below our cities. They seal the entrances to sewers, storm drains, and utility tunnels, protecting both the networks beneath and the people above. They must resist heavy truckloads, corrosive environments, and decades of wear, all while fitting perfectly flush with the road. But how does a manhole cover go from a pile of scrap iron to a precisely engineered product strong enough to withstand the weight of a 40-ton truck? To find out, we step inside a modern manhole cover manufacturing factory, where tradition meets technology, and where every cover tells a story of both resilience and craftsmanship. The journey begins with raw materials. In sprawling factory yards, mountains of scrap iron, steel offcuts, and recycled metal await their next life. Much of the scrap comes from demolished buildings, discarded machinery, and automotive parts. Recycling plays a key role here, not only reducing costs, but also conserving resources. Before the metal can be used, it undergoes a strict inspection process. Workers armed with magnet detectors and visual checks ensure that non-metallic debris, such as wood or plastic, is removed. Consistency in raw materials is vital, since the wrong composition could compromise the strength of the final cover. Once sorted, the scrap is transported via conveyor belts into large bins, ready to be fed into the melting furnaces. But this is only the beginning. The true transformation will happen in the fiery heart of the factory. The furnace hall is the beating heart of the manhole cover factory. Here, massive induction and cupola furnaces generate temperatures exceeding 1500 degrees Celsius, hot enough to turn solid iron into glowing liquid metal. The process begins when carefully measured batches of scrap are fed into the furnace, layer by layer. As the furnace roars, operators monitor gauges and screens, adjusting oxygen and fuel flow to maintain the perfect melting conditions. To achieve the ideal balance of strength and ductility, alloying elements are added: carbon to control hardness, silicon to improve castability, manganese to increase wear resistance. Each addition is carefully calculated, as even slight variations can affect the performance of the finished manhole cover. Within hours, the once jagged scrap transforms into a shimmering molten mass. When the composition reaches perfection, workers prepare for the next step: pouring. While the furnaces burn, another team prepares the molds that will shape the molten iron into manhole covers. The technique used is called sand casting, a method dating back thousands of years, yet still trusted today for its reliability. The process begins with a pattern, a precise replica of the manhole cover, made of wood, plastic, or metal. Workers pack sand, mixed with clay and resin, tightly around the pattern, creating a negative imprint of the cover's design. The mold is built in two halves: the cope, top half, the drag, bottom half. Together they form a cavity into which molten iron will flow. Before sealing the mold, workers press in fine details, textured surfaces to prevent slipping, city emblems and logos to mark identity, raised lettering for manufacturing codes and load ratings. This is not just function, it's craftsmanship, ensuring each manhole cover carries its own unique signature. When finished, the molds are stacked in neat rows, waiting for the fiery metal that will soon fill them. When the furnace is ready, the moment arrives. Workers wearing heat-resistant suits and face shields maneuver massive ladles filled with glowing molten iron. With precision and caution, the liquid metal is poured into the sand molds. The flow is controlled carefully, as too fast to pour could trap air bubbles, while too slow could cause the iron to solidify prematurely. As the molds fill, the red-hot iron hisses and crackles, releasing bursts of heat into the air. Vent channels within the mold allow gases to escape, preventing imperfections. Once poured, the metal begins to cool, solidifying from the outer edges inward, capturing every line and detail of the pattern. In this moment, the transformation is sealed. Cooling is a slow but crucial stage. Depending on the size of the manhole cover, molds may rest for several hours before they are safe to handle. Rapid cooling could cause cracks or internal stress, so patience is essential. When the time comes, workers break open the molds in a process known as shakeout. Sand crumbles away, revealing rough cast manhole covers still coated with blackened residue. The used sand isn't wasted. It's collected, sifted, and reconditioned with fresh clay and binder, ready to form new molds. This closed-loop process ensures sustainability and efficiency. What emerges from shakeout are raw, powerful shapes, manhole covers born from fire, awaiting refinement. Though the castings now exist, they are far from finished. Each cover is still coated with sand and rough edges from the casting process. First, they pass through shot blasting machines. These enormous chambers fire streams of tiny steel pellets at high velocity, scrubbing away sand, scale, and oxidation. Within minutes, the dull, blackened surfaces reveal clean iron. Next, grinders and cutting tools are used to remove excess material, known as flash, from the edges. Workers ensure the surfaces are smooth and safe, eliminating any sharp projections that could cause injury or affect fit. The covers are now beginning to look like the final product, but more precision is still required. For covers that must fit seamlessly with frames, machining is essential. Computer numerical control, CNC machines trim edges to precise tolerances, ensuring that the cover sits flush in its frame. Grooves are cut to prevent rattling under passing vehicles, while bevels are shaped to make lifting easier for utility workers. The precision here is remarkable. Though each cover may weigh 100 kilograms or more, the tolerance is often within fractions of a millimeter. This accuracy ensures not only performance, but also safety. A poorly fitted cover could shift under traffic, posing serious risks. No manhole cover leaves the factory without rigorous testing. Each batch undergoes a battery of inspections. Load testing. Hydraulic presses apply extreme pressure, simulating the weight of heavy trucks. Covers must not crack or deform. Dimensional checks. Engineers measure thickness, diameter, and weight, ensuring consistency with design standards. Surface inspection. Trained eyes search for defects such as cracks, air pockets, or surface flaws. Sound testing. A simple yet effective method. Striking the cover with a hammer. A clear metallic ring indicates solid casting, while a dull sound may reveal hidden defects. Any defective covers are returned to the furnace, melted down, and reborn, ensuring nothing goes to waste. Iron, though strong, is vulnerable to rust. To ensure longevity, most manhole covers receive protective coatings. Traditional covers are dipped in hot bitumen, forming a black, waterproof layer. Modern factories may also apply epoxy coatings or powder coatings, offering enhanced resistance against moisture and chemicals. In coastal or highly corrosive environments, additional treatments such as galvanization or composite inserts may be used. At this stage, city emblems, anti-slip textures, and identification marks stand out clearly against the dark protective finish. The final step is preparation for delivery. Covers are stacked on sturdy wooden pallets, often paired with their matching frames. Each set can weigh several hundred kilograms, requiring forklifts and cranes for handling. Shipping labels indicate the destination, be it a bustling city street, a remote industrial site, or a growing residential neighborhood. Once installed, these covers may remain in service for decades, silently bearing the weight of the modern world above them. If you enjoyed this deep dive into the fascinating world of manhole cover manufacturing, don't forget to hit that subscribe button and turn on the notification bell. We bring you more incredible stories about how the everyday things around us are made, and you won't want to miss what's coming next. Magnets are everywhere, inside your headphones, motors, computers, even electric cars. But have you ever wondered how they're made? And what makes neodymium magnets the most powerful in the world? Today, we're diving deep into the incredible science and industrial process behind how magnets are made. From raw elements to the strongest permanent magnets known to humanity. Before we dive into the fascinating world of magnets, take a moment to subscribe to our channel. We bring you deep behind-the-scenes looks at how the world's most amazing things are made. Every single week, hit that subscribe button and turn on the bell icon so you never miss an episode. Now, let's get started. Magnets are materials that produce a magnetic field, a force that can attract or repel certain metals like iron, nickel, and cobalt. There are several types of magnets: temporary, permanent, and electromagnets. But among permanent magnets, one type stands far above the rest in strength and performance: neodymium magnets. They're tiny but mighty, used in everything from wind turbines to hard drives and MRI machines. So what makes them so special? And how are they manufactured? Let's start at the source. Neodymium magnets are made from rare earth elements, mainly neodymium, Nd, iron, Fe, and boron, B. Despite the name, rare earths are fairly abundant in Earth's crust, but mining them is complicated and expensive. The raw neodymium is usually extracted from minerals like monazite and bastnasite, mostly found in China, Australia, and the United States. Once extracted, these elements are purified and transported to specialized magnet factories, where the real magic begins. At the factory, neodymium is combined with iron and boron to create an alloy called NdFeB. the base for high-performance magnets. The mixture is melted in vacuum induction furnaces at over 1,300 degrees Celsius, 2,372 degrees Fahrenheit. This molten metal is then rapidly cooled into thin ribbons through a process called strip casting. This step is critical. It locks the alloy into the right microstructure for high magnetic performance. Next,